Now that we've talked about the individual gas laws, we want to go ahead and start actually applying some of what we're learning. So how can we actually apply these calculations? We know that we can look at them individually, but what if we want to put them into one equation? We're going to use the ideal gas law to do this. We have the ideal gas law, which is PV equals nRT. Very, very useful. If I can figure out three of my variables, I know my gas constant is constant, I can find the fourth variable I'm looking for. We also have the combined gas law, P1V1 equals N1T1, or P1V1 over N1T1 equals P2V2 over N2T2. We can derive that from the ideal gas law. Excuse me. And then also another equation we can derive, we can figure out the molar mass of a species from its density, or if we can find density if given molar mass. We should know that the molar volume of an ideal gas is 22.4 liters at STP, but again, we can also derive that mathematically and be able to solve stoichiometry problems involving gases. So first, what is the ideal gas law? The ideal gas law tells me PV equals nRT. Some people call it permanent. I personally just say PV equals nRT. And the parameters here are your pressure, your volume, your number of moles, your temperature, and your gas constant. Pressure is reported in atmospheres. Volume in liters, number of moles in number of moles, temperature in Kelvin. And the reason I have those in those specific units is so that I can use this version of the ideal gas constant. Excuse me. Ideal gas constant, 0.08206 liter atmosphere per mole K. Yes, you need to know this constant. There are other versions of the gas constant. We'll even use a different version in this chapter that has different units to it. The number will change as we change those units as we're converting between different units. But you should know this equation, you should know these variables, and you absolutely need to know your gas constant. The ideal gas law is basically combining all of the individual gas laws into one equation. And they're all equal to this constant, Kb, a constant, which happens to be our ideal gas constant, R. We also have the combined gas law. So combined gas law, P1V1 over N1T1 equals P2V2 over N2T2. You can memorize the equation, you can derive it very quickly. Basically, if I rearrange PV equals nRT and solve for R, I know R is equal to PV over NT. Let's say I'm under one specific set of conditions, P1V1 over N1T1, but R is a constant. So under a second set of conditions, P2V2 over N2T2, R1 still has to equal R2. Therefore, P1V1 over N1T1 has to equal P2V2 over N2T2. The T equations are equal, and this is called your ideal gas law. This is called your combined gas law. Three special cases here. Again, I just remember the ideal gas law. I can derive the combined gas law very quickly, and then I can use these special cases as needed. But if we have constant temperature and number of moles, my temperature has stayed constant. So my temperature is constant, so it's not changing. My number of moles is constant, so it's not changing. Notice I get out Boyle's law. P1V1 equals P2V2. If instead of those conditions, I had constant pressure and constant number of moles, my pressure is constant, my number of moles is constant. Notice now what I've got, V1 over T1 equals V2 over T2, which is Charles's law. And at constant temperature and pressure, temperature is constant, pressure is constant. I have V1 over N1 equals V2 over N2, which is Avogadro's law. So the ideal gas law can get you the combined gas law, can get you all the individual gas laws. Again, I don't prefer to memorize them individually. I prefer to memorize the one and then be able to derive the others. You can do what you would like, but you are responsible for all of these laws. Let's work some examples on how this actually works. A sample of gas has a volume of 2.80 liters at some unknown temperature. When the sample is submerged in ice water at 0 degrees C, its volume decreases 2.57 liters. What is the initial temperature of the gas in Celsius? So I'm given a volume at some unknown temperature. I'm given a temperature and a new volume, and I want to know the initial temperature. If I think about my combined gas law, P1 V1, excuse me, over N1 T1 equals P2 V2 over N2 T2. Notice it never mentions the number of moles here or the pressure of the system. We can assume that the number of moles are staying constant. We can assume that the pressure is staying constant. Why? Because it doesn't mention it. So that's the only assumption we can make, is that it must be constant. Therefore, V1 over T1 has to equal V2 over T2, which is Charles's law. But remember, his law requires Kelvin temperature. I'm going to rearrange this equation to solve for T1, assuming this is V1, T2, and V2. If I rearrange this equation to solve for T1, T1 would be equal to V1 times T2 over V2. Again, if you don't understand that, it's just algebraic manipulation, come see me for help. V1 is 280 liters, or 2.80 liters. T1 is we're trying to find. T2 is 0 degrees Celsius, or 273.15 K. We need this in Kelvin. Charles's law is valid under absolute temperature conditions, which is Kelvin scale. Divided by 257, or 2.57, I apologize, I'm getting tired. 2.57 liters gives me 297 Kelvin. I'm going to convert that to Celsius by subtracting, so minus 273.15 to get to Celsius, 24 degrees C. Remember, subtraction, we're going to keep it to the least precise measurement. This is precise to the ones place, so precise to the ones place. So 297 Kelvin gives me 24 degrees C. My final answer here, 24 degrees C. Second example, we have a cylinder with a movable piston and has a volume of 7.25 liters at 4.52 atmosphere. What is the volume at 1.21 atmosphere? So I've got a volume and a pressure and a new pressure. I'm going to use my combined gas law, P1 V1 over N1 T1 equals P2 V2 over N2 T2, and assume that my moles are constant and my temperature is constant because it didn't say anything otherwise. I'm then going to solve using P1 V1 equals P2 V2, so Boyle's law. I've got P1, I've got P2, I've got V1. I'm going to solve for V2. V2 is equal P1 V1 over P2. P1, 4.52 atmosphere. V1, 7.25 liters. P2, 1.21 atmosphere. Be careful on these problems. Make sure the units are matching up. This is both in atmosphere, so they can cancel. If they weren't, I would have to convert to the same units. 27.1 liters is my answer. So a cylinder with a movable piston has a volume of 7.25 liters at 4.52 atmospheres. If the pressure was decreased to 1.21 atmospheres, the volume would be increased to 27.1 liters. No surprise, volume and pressure are inversely proportional to one another. If I decrease the pressure, the volume should increase. Okay, what volume does 2.105 moles of ammonia gas occupy at 25 degrees C and 0.980 atmosphere? This one I'm going to go ahead and use my ideal gas law. Why do I know I'm using the ideal gas law, not the combined gas law? Because I'm just given volume. I'm told I want to know volume. I'm given number of moles. I'm given a temperature and I'm given a pressure. I'm not taking a sample and changing its conditions. I'm just asking about something for one specific gas at a set of conditions. So PV equals nRT. My pressure, 0.980 atmosphere. my volume, what I'm trying to find. Number of moles, 2.105. R is my gas constant, 0.08206 liter atmosphere per mole K. And my temperature is 25.0 degrees C, but I know I need that in Kelvin, so it's going to be 298.2 Kelvin. 0.2, because this is precise to the tenth place, the first decimal place, so this must be precise to the first decimal place as well. I'm going to rearrange my equation. Volume is equal to nRT over P, and then plug everything in. 2.105 moles times my gas constant, 0.08206 liter atmosphere per mole K, times my temperature, 298.2 K, divided by my pressure, 0.980 atmosphere. If everything was plugged in correctly, your units should cancel out appropriately. Kelvin cancels, moles cancel, atmospheres cancel, and I'm left with liters, which is what I wanted. Volume, 52.6 liters. So the volume of 2.105 moles of ammonia gas at 25 degrees C and 0.980 atmosphere would be 52.6 liters. We do have an ideal gas law deviation as well. We can find density. So the way most students memorize this, I actually learned this mnemonic from Dr. Fry, and I really like it because it helps me memorize it. Dr. Fry, for reference, was her dad was in the military, so they moved a lot. So her reference for this is density equals military, police, R, terrific, MP over RT. So I'm going to show you the derivation of it. You're not responsible for the derivation. I'm going to show that some students feel better about it when they understand where the equations are coming from. But this is what we've got going on here is the capital M here represents molar mass, or grams per mole. We've got a lowercase m that factors into the equation using just mass and grams, but the capital M here means molar mass. So molar mass. This is pressure, grams per mole, atmosphere. R is my gas constant. So liter atmosphere per mole K. And T is the temp in Kelvin. And density here is grams per liter, which is a little bit different than normal. How did I get here, though? Again, if you don't care about the derivation, skip this part. I don't care. But some students need to see it. So we know molar mass, which I represent with that scripted M, is grams per mole. We're going to rearrange this equation. And this is also, so we can say mass per N, because N represents number of moles. We're going to rearrange this to solve for N. N is equal to your mass over your molar mass. When run over space, we know the ideal gas law is PV equals nRT. So we're going to substitute this in for a number of moles. PV equals our mass over our molar mass times RT. We're going to rearrange this equation, and we're going to solve for molar mass. We're going to say molar mass is equal to mass times RT over PV. But I'm going to rearrange this one more time and say, well, I could also say that this is equal to mass over volume times RT over P, because these are equivalent, right? But remember, density is equal to mass over volume. So this represents density. So really we can say molar mass is equal to the density RT over P, which if we rearrange this, density is equal molar mass times pressure over RT. Again, you don't have to know this. I won't require you to know the derivation, but some students do better knowing it. So if it helps you, fantastic. If it doesn't, memorize military police are terrific, and memorize this, and you can derive it the other direction. Let's look at some examples we can use with this though. Sample of gas with a mass of 0.311 grams per grams and a volume of 225 mils at 55 degrees C and 865 millimeters of mercury. Calculate the molar mass of this gas. A few different ways we can do this. We could just solve for a number of moles and then take the mass of the substance, or we could plug it into the equation. Let's just do it both ways. First, let's just solve for a number of moles. P equals nRT. We've got grams here. We're going to deal with this in a second. We got your volume, 225 milliliters, which is the same as 0.225 liters. 55 degrees C, I'm going to convert to Kelvin, 328 Kelvin. Again, I just took that 55 degrees C and added 273.15, but because of sig fig rules, I have to keep to 0 decimal places the ones position. And 866 millimeters of mercury, 866 millimeters of mercury in an atmosphere. I know 1 atmosphere is 760 millimeters of mercury, so this equals 1.14 atmosphere. So the first I'm going to solve this is I'm going to determine N, which is the number of moles, and then determine molar mass. And then I'm going to erase it and show you the other way to do it just in one equation. So N is equal to my pressure, 1.14 atmosphere, times my volume, 0.225 liters, divided by my gas constant, 0.08206 liter atmosphere per mole K, times my temperature, 328 K. Kelvins have canceled. Atmospheres canceled, liters canceled. Now the moles down here is the denominator of a denominator, which makes it the numerator. And I don't actually have this answer written out, so 1 second. 1.14 times 0.225, divide by 0.08206, divide by 328. This gives me 0.00953 moles of sample. Be careful when you plug this in your calculator. I have to plug in 1.14 times 0.225 divided by 0.08206 divide by 328. Students want to hit a multiply sign right here. Don't do that unless you're using parentheses properly. It's easier to plug it in this way. You're dividing that quantity by 328, not multiplying, or you will get the wrong answer. Now that I have that, I can find my molar mass by taking that 0.311 grams divided by 0.00953 moles. And I get 32.6 grams per mole. So that's absolutely one way you can do it, and it's completely valid. But we can also do it by just rearranging the density equation. So if you need to pause the video, please pause, so I'm about to erase everything, or most things. Don't want to erase that because I want to write it. So the other way we can do it is rearranging that equation. Molar mass is equal to density RT over P. But density is equal to mass over volume, RT over P. The mass is 0.311 grams. The volume is 225 liters. Gas constant, 0.08206 liter atmosphere per mole K. Temperature, 328. And pressure is, 1.14 atmosphere. Atmospheres have canceled. Kelvin has canceled. Liters has canceled. I've got grams per mole, which is what I'm looking for. Like 32.6 grams per mole. So same answer, which is good because, math works out that way. It should be the same answer. But you can do it either direction, whichever way makes more sense to your brain, okay? What about this next example? Calculate the density of a sample of chlorine gas at 25.04 degrees C and 759.2 millimeters of mercury. I want density, and I know density is military police are terrific. So, I want the density of chlorine gas. What is the molar mass of chlorine gas? Trick question, right? Chlorine is Cl2. 70.90 grams per mole. Pressure, 759.2 millimeters of mercury. You can do that in the same equation if you would like, or you can do it separately. 759.2 millimeters of mercury, 1 atmosphere, 760 millimeters of mercury. If you don't know how to do it in your calculator properly, please do it separately and then plug it into this equation. I know some of your calculators are not as fun to work with. Divide by RT. R is 0.08206 liter atmosphere per mole K. And temperature, 25.04 degrees C plus 273.15 brings me to Kelvin. So my kelvins are canceling here. Denominator of the denominator and denominator of the numerator cancel out here. Atmospheres cancel out here. Millimeters of mercury cancel out here. I've got grams per liter as my unit. 2.894 grams per liter. This is 4 sig figs. This is 4 sig figs. This is exact. This is 4 sig figs, and even after addition, this becomes 5 sig figs. So final answer, 2.894 grams per liter. A 3.50 gram sample of a diatomic gas in a 1.5 liter container has a pressure of 2.42 atmospheres at 355 K. Determine the identity of the gas. So I like questions like this. I like questions that make you determine the identity of things because it makes you think outside the box a little bit. The easiest way to determine the identity of something is either figure out the molar mass or do a chemical test. Well, you're not obviously going to do a chemical test when you're sitting here, doing calculations like this. So best thing, determine the identity of a mass of the gas is find molar mass. I know the molar mass is equal to mass over volume times RT over P. It tells me I have a 3.50 gram sample in a 1.5 liter container. Again, writing this like this represents my density. I could also do PV equals nRT, solve for N, and find molar mass by taking the grams divided by N. It's going to get you the same result. R is 0.08206 liter atmosphere mole K. The temperature here, 355 K. And the pressure, 2.42 atmosphere. Plug all that in, and I'm going to get an answer. Sig figs, there's two sig figs here, 28 grams per mole. Now I look at my possible answers here, and I'm like, oh look, they're all diatomics, which means this mass is the molar mass of a diatomic. Again, it does say diatomic here as well. So I have to divide this by 2. I get 14.01, which is the molar mass of nitrogen. Or sorry, the atomic weight of nitrogen. The molar mass of N2 is 28.02 grams per mole. So I know that this is N2. Well, this one, the four most common gases in the atmosphere, N2, O2, argon, and CO2. Assuming all gases are in containers of equal size, temperature, and pressure, which gas has the highest density? Do they all have the same density or not? Probably not if I'm going to ask you the question. But let's logic our way through it. What do we know about density? Density is your mass over your volume. If all gases are the same volume, pressure, and temperature, the sample with the highest mass will have the highest density. So let's find their masses. N2, 28.01 grams per mole. O2, 32.00 grams per mole. Argon, 39.94 grams per mole. And CO2, 44.01 grams per mole. Because they all have the same temperature, pressure, and volume, we can assume it's just going by mass. CO2 will have the highest density. What volume in liters of methanol gas, CH3OH, at 287 Kelvin and 1.0 atmosphere will be produced from 5.40 liters of CO2 at 324 K and 3.88 atmosphere and 8.95 liters of hydrogen gas at 355 K and 412 atmosphere? So I've got 324 K, 5.40 liters. Let's see, volume. I want volume here. 287 K, 1.09 atmosphere. And 3.88 atmosphere, 8.95 liters. Trying to pair up the pieces so we can connect them. 355 K, 4.12 atmosphere. You may not recognize it right away, but because you are given volume, temperature, and pressure of each reactant, this is a limiting reactant example. Because those three pieces of information can get you the number of moles of each species. So, let's go ahead and figure out what we have. First, we're going to find the number of moles of CO. Use ideal gas law, PV equals nRT. So I know number of moles is PV over RT. The pressure of CO is 3.88 atmospheres. The volume of the carbon monoxide is 5.40 liters. My gas constant is 0.08206 liter atmosphere per mole K. And my temperature is 324 Kelvin. I calculate that out and I get 0.788 moles of carbon monoxide. Do the same thing for the H2 gas. Number of moles of H2. My pressure is 4.12 atmosphere. My volume is 8.95 liters. Gas constant 0.08206 liter atmosphere per mole K. Temperature 355 K. My number of moles here, 1.27 moles of H2. Now students want to compare the two numbers right here. You cannot compare these. The reaction is not 1-to-1. I need to see what's actually limiting based on what would be used up. So over here I'm going to write number of moles, CO needed to react all of my H2. I have 1.27 moles of H2. 1 mole of CO is consumed for every 2 moles of H2 consumed. 1.27 divided by 2 gives me 0.632 moles of CO needed. I have 0.788 moles. So I ask myself, do I have enough? I need 0.632 moles to react all of my hydrogen. I have 0.788 moles of CO2, or of carbon monoxide, CO. So yes, I have enough. This is my excess reactant. This is my limiting reactant. My H2 is limiting. So with that, I'm going to find the number of moles of methanol I can make. I'm starting with 1.27 moles of H2. 1 mole of methanol is produced for every 2 moles of H2 consumed. Gives me 0.633 moles of methanol produced. Very close to done. Now I just need liters. Remember PV equals nRT? Well, V is equal to nRT over P. 0.633 moles times the gas constant, 0.08206 liter atmosphere per mole K. And my temperature of my methanol is 287 Kelvin. Pressure 1.09 atmosphere. Volume 13.7 liters. So lots of work there, but I'd be able to produce 13.7 liters of methanol based on these conditions. And the last example, the Haber process. The Haber process is just a fancy name for this reaction. The Haber process synthesizes ammonia at elevated temperatures and pressures. Suppose you combine 1,583 liters of nitrogen gas and 4,595 liters of H2 gas at STP. What does STP mean? Standard temperature and pressure. One atmosphere, 0 degrees C, which is 273 K. Heat the mixture to run the reaction, then separate the ammonia from the reaction mixture. What volume of reactant measured at STP is left over in liters? Assume the reaction goes to completion. So it is still a limiting reactant problem. I just want to know how many liters of excess remain at the end. Let's find the number of moles of N2. Again, we're rearranging PV equals nRT. So N is equal to PV over RT. Pressure is 1 atmosphere because we're at standard conditions. Volume is 1,583 liters. R, 0.08206 liter atmosphere per mole K. Temperature 273 Kelvin. To not limit safe things, you should probably write 273.15 Kelvin because this is written to 4 sig figs. So let's keep it to 4 sig figs. 1 times 1583 divided by 0.08206 divided by 273.15, 70.62 moles of N2. So I can make 70.62 moles of N2, or that's how many moles I would have in that system if I had that many liters under those conditions. Same thing for hydrogen, number of moles of H2, 1 atmosphere, 4595 liters, 0.08206 liter atmosphere per mole K, 273.15 K. So 1 times 4595 divided by 0.08206 divided by 273.15. N of H2, 205.0 moles. So again, I can't just look at those numbers of moles though and tell you which one's limiting reactant. I have to compare the two. So how many moles of N2 do I need to react all of my H2? I have 205.0 moles of H2. I know I have 1 mole of N2 reacting for every 3 moles of H2 reacting. 205.0 divided by divided by 3 gives me 68.33 moles of N2. And I ask, do I have enough? I have 70.62 moles of N2. I need 68.33 moles of N2. So yeah, I have enough. My N2 is my access reactant, my H2 is my limiting. I'm going to take the difference between these two though to figure out how much excess I'm going to have left over. I will have 2.29 moles of N2 in excess. I need to know how many liters that is. Liters of N2 excess. Again, PV equals nRT. V equals nRT over P. I have 2.29 moles. Excuse me. 0.08206 liter atmosphere per mole K. Temperature is 273.15 K. Pressure is 1 atmosphere, because again, I'm under standard conditions. So 2.29 times 0.08206 times 273.15 divided by 1 gives me 51.3 liters of N2 remaining. I ended up with 3 sig figs because the subtraction here gave me 3 sig figs. So I'd have 51.3 liters of N2 remaining at the end of the reaction.